Welcome everyone from my side as well. I'm tremendously honored and excited to kick this off. And it gives me the opportunity to talk about something a bit more high level, something a bit more conceptual. So let me tell you what to expect from me in the next 30 minutes. So QHack celebrates the idea of quantum computers being useful. So in some sense, the field of quantum applications. And quantum applications research is not that old, and it's part of this transition from quantum computing from a theory discipline in academia to actually an emerging technology. And for any field, this is actually a very challenging transition because the theoretical constructions people have developed in academia have to be challenged. They have to be extended by new methods. For example, the idea is that we now have new devices that we can test stuff on. The idea is that we have new requirements like practical utility that set new standards. And a lot of the work in quantum applications is like kind of playing with these elements and closing the gap. And in my personal view, it means also to tear down a lot what we thought was the way to go. So here I want to talk about a very specific aspect of this that I think about a lot, which is a bit of a controversial question. I want to ask if the favorite narrative of quantum computing, the story of quantum advantage, is actually the right tool to think about quantum applications. And what I mean about quantum advantage is hidden in almost every paper. It's in sentences like better than its classical counterparts, or polynomial speed up, exponential speed up, the idea of quantum supremacy. I'm sure all of you and myself who write papers have put this everywhere, either to convince the reviewers or just because you felt like this is kind of the way that papers are written. And my main argument is that we only have very limited tools or very limited methods to actually convincingly show these quantum advantages in practical quantum computing, and should maybe focus more on the groundwork. And then maybe one day from another point of view, look at the advantages again. I will do this using my own backyard topic. As Nathan said, I've worked a lot in quantum machine learning research, so the idea of using quantum computers to learn from data. I think that a lot of the things I say might apply to other fields as well, but I hope as a side effect you also learn a bit about quantum machine learning if you're not in this field already. So QHack is a little bit of a different type of beast, so I thought I'd do something a bit strange. I'm a bit nervous if this will work, but I'll read a story to you, and I hope you understand what the story actually means. So once upon a time, there was a land, desert land, and the people of desert land, they loved being where they are because they grew up around a whole bunch of myths of a strange and beautiful fruit that's called Q. And the people of desert land believe that when someone eats Q, then they suddenly can do their work a lot faster. And well, after years of only hearing about Q from the priests and from the philosophers, some wild Q fruit trees were actually found and shared amongst the people. And the dream of the desert people was to cultivate and to harvest Q on a mass scale, and to use it to make basically the world a better place, of course, and to get pretty rich as well, which is always a nice side effect. And so the people of the desert, they kind of started to sail out and had their first little kind of wild quantities of Q on their boats. And they wanted to find ways of putting them to use and of trading them. And one of the expeditions that we're talking about today was going to another island, a green island, that has recently discovered another plant, which is called the ML, which is kind of moss, I think. And when you eat it, ML gives you an absolute superpower. And it was therefore sought after all over the world. And the people from ML, they were already very influential and very, very powerful and quite rich as well. And now I'm so excited about the prospects of combining Q and ML. The desert people set their camps up at the shores of the Green Island. And then two different people in this team of explorers emerged. The first type of people were the philosophers again. So they were in the tradition of the old philosophers, and they tried to find logical arguments of why QML should work. So to give you an example, one of the philosophers was very famous for finding that on a Tuesday, when the moon is full, a relatively small person of 12 years should do a task of sweeping quite a bit faster than when only eating the ML moss alone, as long as the floor is really, really large, and if we have an oracle telling us something about the size of the broom. This was quite nice, but no one really understood what this really means for sweeping floors, right? And then there was another group, and those were the alchemists. And they just threw both the ML and the Q into a pot and saw what happens. And also there was a bit hard to tell what really happens because, sometimes like when someone ate this QML thing and mixture, they were a bit faster at doing something, sometimes they weren't, something was a bit better, but kind of like the quantities of Q were really, really small. So we didn't really know what this was about. And lastly, the inhabitants of the Green Island. So this is not a nasty colonialist story, luckily. So they were actually like quite happy with this little camp here, and they were quite unimpressed because they were busy making a lot of money. And their fruit was also working so well that they actually didn't have use for anything extra. They'd much rather actually someone tell them why it works so well. So that didn't discourage the desert people though. So they kept talking about the promise of QML. And so obviously, you know what I'm talking about. And I want to just break down this little metaphor with you. So this is also for people who are, I think a lot of you are maybe not from quantum applications, quantum computing research. So where are we actually now? Obviously, this little story, the people of the desert islands, so the people that made the Q, they come from this tradition of like having had years of research into something we call fault-tolerant quantum computing. And this is kind of an idealized idea of how we can harness the power of quantum information for algorithms for computation. And in recent years, as many of you know, we had this like revolution of having the first scale devices, so have the first small wild quantities of Q. They are very impure. They're very like different from what we thought we would get. And so these two different viewpoints are really not a clash, but they're really different paradigms of how to do research. So the fault-tolerant version thinks of the basic building blocks of quantum computers, of qubits, as being there in abundance. Computations are exact, so everything works like the maths we're doing. Errors are corrected, you could say. So physical errors that devices will make. And then the algorithms that you all know, Shor's algorithm, Grover's algorithm, HHL, they're all kind of developed and measured by a very specific measure. And I think not everyone is very clear about that this is very specific. And this measure I would refer to as computational complexity. So this is a measure of how the resources you need for computation, the number of qubits, the queries to an oracle, the runtime, number of gates, grows with the problem size. And this is also a statement that's asymptotic. So it's a very, very rough kind of lens we put on things before we even know anything about our computers. The near-term computers, as you know, we have a lot of qubits. A lot of you will have tried and will try to experiment and realize how limiting that this actually is. Also, the results are constantly wrong because we can mitigate error, we can't really correct them. And so a whole entirely new idea or paradigm of computation has emerged, and this is the paradigm of variational circuits. And the idea is if we don't know how to build algorithms for these small qubit numbers, we basically just define parameterized families of algorithms, and then we add an optimization problem to the whole mix and just find the best algorithm within that family. And very much the paradigm is now run it and see. And also, if in following talks you don't get confused, so basically these near-term devices where we have access to them at the moment, so you can run them on your local machine as simulators. When you reach like 15, 20 qubits, depending on your machine, depending on your application, it's really painful. So then you might want to outsource them to remote simulators that are parallelized. And then obviously there's also remote hardware access from a lot of companies and a lot of labs. So this is really beautiful. So sometimes the requirements are a little bit different, but all of those are quite limited in what you can do in realistic algorithms at the moment. And so what this all means, or what I want you to take away, is that if you look at the set of all algorithms you could run on a quantum computer, we have two very, very small windows. So maybe I should have drawn them overlapping. I wasn't actually too sure about it. The one window is on these very small-scale experiments we can do with our prototype devices, and the other ones are the algorithms we can talk about in terms of this complexity analysis. But they're small windows. They're not the truth of what's all possible, which is something we will explore probably in the next decades, which is so exciting. Okay, in quantum machine learning now, our goal is, I also want to characterize our goal basically, and do this in a very simplistic setting. Machine learning means to generalize from data samples how to perform tasks with computers. And the way you can think about this is always that there's an underlying distribution of data. Your data can be, for example, old school data like census data of people, or it could be clicks of user behavior, images, text, whatever. And so what you get given is a couple of examples of this data set sampled from the distribution you assume. And machine learning has different tasks, and also some of them are a bit more complicated than what I sketched now. For example, I don't talk about time here, or I don't talk about reinforcement learning where an agent influences the distribution, and so on and so forth. But so some of the tasks could be, for example, clustering, where you need a notion of distance between data to, like, say which ones are from the same type. There is this task of data generation, generative models. You might have heard of GANs, where I want to sample from the same distribution. And here I try to like put this here, so these data samples lie in very high dimensional spaces. So this image is very misleading. You do not have full knowledge, or you don't have full cover of your space from the samples. Actually, almost everything of your data space or your distribution, you have no clue from data samples what's actually happening there. So for example, here in this area, you might want to sample from here, but you've never seen a sample. So a lot of structure needs to be in problems to actually make them solvable. It's actually an interesting part. Anyway, we're not talking about classification, which is a part of supervised learning, in which you have extra information. You don't only get given data samples, you also get given their classes. The reason why we talk about supervised learning so much, so it's one of my favorite topics, but it's also that if you look at machine learning theory, statistical learning theory, it talks about this case a lot because we have a lot of information on what's good here, and that's quite helpful. Okay, cool. So what I want to do, I want to take this problem, I want to formalize it. So a few equations, but I'll explain this. And then I want to show how quantum can be injected into this problem. And then I want to talk about why advantage is so really, really hard in this whole setup to talk about. So we get given, or we assume that there's this probability distribution, and now the labels, we often assume that they are generated by some ground truth function that tells us which parts have the label red and which parts have the label green, for example. What we get given is a couple of data samples, as I said, together with the labels, and two things that we kind of get given, but as a modeler, we choose them ourselves. This is a class of hypotheses, a class of functions that we want to say are candidates for like the ground truth that we actually want to find, but which we don't know. And then there's a loss function, and this loss function somehow compares what the ground truth says about a data sample and what our candidate says about the data sample. And now this is our goal, and it's actually quite beautiful if something as real life, so really as application from real life as machine learning is, you can actually write it down as an equation. So what we want to do in one formulation of machine learning is we want to find the model that minimizes a certain quantity over this model class. And the quantity is a loss integrated over all the data. So basically the average loss over all the data you could see. And then we weigh it by this probability distribution. The meaning of this is just like if we have a region where we don't really sample data, we don't need our candidate model class to be really good. So we just say, okay, the ones we care about, the regions, we want to be really good with this loss. And also here's the problem about machine learning. And this is already why machine learning might not be a problem like prime factorization, like structured, unstructured search, like, you know, these things that have been traditionally looked at in quantum computing. The goal we want to like, or the thing we want to optimize here, we don't have access to it. We do not really know about this distribution. We do not really know the ground truth. We can write it down, but this is like stuff that's not given to us in a real problem. Even if we were, because we're in academic fantasy land or something, then this integral is like extremely difficult to solve. So what we do is something that's called empirical risk minimization, and we find a model that basically just like optimizes this integral, but a finite sample approximation of this interval, which just means, so this is what you do when you have training data in machine learning, you fit your model to that training data. And then you hope for the best. And this is really important here. You solve a proxy problem in real life, and then you don't really know what it does to your real problem. And a lot of machine learning research really finds out kind of what are the guarantees when I solve this? What are the guarantees on my real problem? Okay, cool. So how does quantum computing come in? I want to show you like three, which I think is the three dominant ways of how you can inject quantum computing. This one was the one that people started off with very early. And it's kind of what quantum computing researchers always did back in the day, is they take an algorithm, they outsource it to a quantum computer. In this case, very often we're thinking about the fault-tolerant, theoretical machines. And then they just show that something goes faster in terms of this complexity, this asymptotic complexity. And what is here important is that this only touches kind of my execution in some sense. So the problem completely stays the same. So I would say there's very little ML in the QML research here, but it's obviously, you could find some speedups and examples. Yes. The second one was is this whole like kind of near-term approach to quantum machine learning. And what you do here very often is people have started realizing that if in near-term variation circuits, we have actually model families, and these model families even have these beautiful parameters so we can optimize in this class. Why don't we just use these quantum computations as a model family, so as a family of hypotheses? And the interesting part now here is that the entire problem changes, so not only the execution of the problem, and you really have to start rethinking everything. For example, you cannot just depend on what machine learning people say about how your proxy problem solves your original problem. You have to like start making these arguments from scratch for these model classes. So something is really interesting is going on here. Also, because you will see this quite a lot, just to show you like how a quantum computer could do this. For example, it could encode data into some kind of like quantum circuit. So these, if you've never seen a circuit kind of diagram, then good luck. There will be a lot of those like in the talks, I assume. And then you have another part of the quantum circuit. So these are these blocks that is trainable. And then you measure something, you get a lot of results. You average some kind of over these results, you get a number, and this number you interpret as a label. If you're more the visual type, for 1 qubit, you can actually plot what happens if you do something like that. You encode data, kind of like your trainable circuit varies the data or turns them around, and then you define some kind of decision boundary or some kind of regions in your quantum state space. Now there's a third kind of approach to quantum machine learning which becomes louder and louder. I have sometimes the feeling when the first two were a bit disappointing or people get bored by them, they just now start to like talk about the third one. I think it is very, very, very early days for this one. And this is this quantum data notion. So you basically say the data itself is our measurements from a quantum experiment, or they even quantum states, and I start acting. So I could make a lot of things red here as well. So I could make the model class again red and say this is like done by quantum computers, but really change even the deepest basis of your problem, which is quite interesting. But yeah. This references should be here. I also have to say that the references are always like referred to archive numbers. So if you Google them, you should find the papers. But this was actually coming from the first slide. Okay, cool. And then, I just have to basically now draw this argument, or I can use this setup now to say, why are quantum advantages for machine learning so hard to find? And as a reminder for me, this is really a kind of like indicator also why applications are so difficult to deal with under this idea of advantages and complexity here and the tools we have actually given. I want to give you 3 arguments. The first one is that I think for the problem we just looked at, computational complexity theory, it might be the wrong tool. The second one is that benchmarks are that we could do that we get kind of like from machine learning, people in machine learning love doing benchmarks, are very limited at this stage just for the devices that we have. And I think also the interpretations we can draw are very limited. And the third one is we could now, obviously, as a machine learning theory, it's very beautiful. We could now inject quantum theory and build a new quantum machine learning theory. But machine learning theory is changing at the moment drastically. So it's very hard to actually know where to inject at the right time. So that's a very interesting part that's maybe very unique for quantum machine learning in this case. Okay, cool. So let me go through these arguments. And I'll just like show you the slide now of the first kind of approach to quantum machine learning. So where's the problem here if I kind of try to speed up or make this faster, the model evaluation or my optimization algorithm in my proxy problem that I solve? The problem is that machine learning is really good, really good. And this was like part of the story, as you saw, like that the people from the Green Island or the people who like harvest machine learning, they're not actually so interested in speeding things up. They work, they're exporting, they become rich. But so, and to give this a bit more of a concrete number, so if you train, for example, deep neural network with stochastic gradient descent, which is a method that's done all the time, the optimization runs linear in the size of the data, and the model evaluation runs linear in the size of the parameters. If not, you could almost like stop everything already, because we have millions of parameters, millions of data points in modern day applications. And so quadratic scaling is totally out of the question here. If everything is linear, the only thing you can do if you want to have a speed up, you can try to do something sublinear. And then you have to start like inventing oracles. So this is why I said in the example, like, only if we ask the oracle from next door if the broom is so and so long. So you have to really make assumptions on how you load data then. And there was this like interesting point in quantum machine learning in this part of research where people found out that if you take the same assumptions for classical machine learning, you can do quite a lot more as well. No one knows exactly how realistic they are, and so on and so forth. In the second kind of way of thinking about quantum machine learning, you also face a couple of problems. So there's actually a few of them. So the first one is that to show your advantages and your kind of quantum speedups, you need to really be very clear. So you cannot only take like the model class and say, oh, we can't really run this on a classical computer, so now learning is has a quantum advantage here. You really have to be careful. You have to show that the quantum computer also learns, so it can solve this problem. You need to show that this problem solves the original problem. So you have to do many, many steps. And I think people have become better and better at making these proofs more and more watertight. But even then, there is something that always disturbs me. And I sometimes wonder if I'm the only one who's disturbed by this. And this is that the way that often we make these like very artificial proofs is that we kind of construct a distribution of data and also a labeling function that's really artificial. It's constructed from quantum computing, basically. Why is this a problem? So it gives you nice existence proofs. But why is this a problem is that machine learning has these no free lunch theorems. In machine learning, it is known that you can always if you have a model, it will always run well on one data set, but you always have a data set where it runs badly on. Or the other way around, if you've got a data set, you always be able to construct a data set so that the model works well. So it's not a surprise that we find cases where quantum computing works well. The question is, does it work well for stuff where we actually want to use quantum computers in a few years? So I think we can research a long time and construct artificial problems and actually not come closer to this question of quantum applications. I'm not talking about having fun with proofs, but I'm talking about really using quantum computers one day. So this is, I think I will submit this to the meme contest. So this is kind of what I think we sometimes do when we look at computational complexity and quantum computing. I'll wrap up now, but I just want to come to the other two arguments. And this is the other argument is about benchmarks. Benchmarks are already, we use them because machine learning people use them. There are these tables when you just run a small problem and then you just report absolute numbers. So this is how long it took. This is what so usually we report on something called the test error, which is you use some data you haven't seen before and just see if your model does well on this data. And so lots of our papers have these kind of tables or these kind of plots at the end. And besides it being really hard to say something very general from an example that I just run, so you need a lot of those examples, we have the problem that our benchmarks have to be very small. So we have to reduce the data set to something extremely small to get them onto our simulators or devices. And in the regimes where we run the benchmarks, they're not the regimes where we actually want to talk about learning. So we might actually probe something completely different from where machine learning acts. And I see very few studies where this is actually questioned or investigated, what errors do we make? What scope do our experiments actually have? This is also very, very tricky. And the third one is that this theory building sits on shifted ground. And this is also interesting. So in machine learning theory, for a long, long time, people have thought that basically that very simple model classes are kind of the best thing to do. In simple model classes, we solve the proxy problem not too well. So this thing called training error, which is kind of how well we minimize, is not too good. But we know that the real problem will also be in a similar area after we train models. And then we have very, very rich model classes. So we kind of if we solve the proxy problem too well, we know that our original problem won't be too good. What we see now, recent years, this is why you have machine learning on your phones. We see that actually both the proxy problem and the real problem are solved very well. And people are wondering at the moment why. And so if you build quantum computing now into this kind of theory, it's very hard to actually know where you end up. This is a very interesting part of the field, but it's really hard. Okay, cool. So I'm kind of wrapping up. I think that in basically coming back to the story, you could have two different ends. You could say that maybe if we continue always pushing for these advantages and selling that our Q will be better and it will make ML better, we might actually give up at some stage because we get bored and no one really listens to it, and then we set sail back home. But I think there's an alternative ending to the story, and which is that maybe we start kind of like talking a bit more to the people of the island. We stop kind of trying to just sell something. We actually start kind of growing fruits together, or like we think about other things. And maybe one day we find out that there's a tree that grows with the moss and there's a new fruit and actually just tastes really nice, or it is very nutritious and can like, like feed a lot of people. And so I just want to like put these three alternative questions to maybe ask, except from quantum advantage. For example, where do quantum theory and machine learning fit together? There are a couple of beautiful examples of theory that explore each other and that really accelerate our research. One of my favorite examples is the connection between quantum kernels and kernel methods in machine learning, or the idea of quantum gradients to train deep learning pipelines. We can also go back and ask really what quantum effects do to change the problem of learning. So get a little bit more into foundations again. And then one of my favorite questions is, what are actually good toy models that take the complexity out of the stuff we're doing, but still keep the essence, which is what physicists love doing, right? So these are, for example, alternative questions I throw out. Thanks very much. If you love this type of critical thinking and thinking a bit out of the box, also get in touch with us. We're always looking for people who are a bit adventurous here. Yes, thanks very much, Nathan. Over to you.
Amazing, Maria. Thank you very much for that awesome talk. I did have one quick question I wanted to jump into right after your talk. You said there's these two camps. Which camp would you say that you come from?
I definitely come from, no, oh gosh, this is really hard. Maybe there was another camp that kind of like starts, so I think my brain was never really like working with the philosopher camp and the computational complexity camp. So I was kind of never really like trained by a person who sits down and shows me how to prove error bounds and stuff like that. And I always like lose interest after like a couple of days of doing this. And a couple of people tried to do this with me, but I'm just like, okay, let's go out and do something fun. I'm also like the benchmarks. I also tried this for a while. I'm also not very good at it. I love this, like maybe the third camp that would go and talk to the people from the Green Island and tries to like understand how they do their things and just like how to inject our stuff into this, and maybe more that type of camp. You're right. I should have thought about this like before.
All right, chat. We will bring your questions to Maria shortly, so please put those questions in the chat for us. In the meantime, Maria, I did want to ask you a couple more kind of fun things. We were talking backstage. You're an old veteran now of QHack. You've been with us a number of times, streaming live. You've given many online talks over the years, but I heard that recently you had a pretty unique experience giving an online talk. Would you care to share with our audience?
It was a moment of where I really knew, when there's a moment when you really know you've got your stuff down and people can wake you up in the middle of the night and it kind of like works out and you never have to be scared anymore of talks. There was a moment when I was just preparing for actually quite a big talk, which was like, I still had an hour. Suddenly I get an email and the email sends me just a link. We're waiting for you here. And I clicked the link. It was a Zoom link. And the only thing I hear is like, Dr. Schuld is like joining us. Dr. Schuld, we're so happy, we're waiting for you. But now you're here. We're really looking forward to your keynote. And I had no clue where I was and what keynote to give. And so I kind of pretended I had technical issues. I kind of looked through my emails and I had a talk I had to give like a couple of days later. And it turned out it was this crowd, but for some reason they hadn't told me, but there was some kind of like pre-event that I was supposed to give a keynote up. I looked through my talks, I just put up a PDF. I had no clue which one it was. I just skipped the first slide so they couldn't see the intro. And then I just gave this talk for an hour and I said bye. And then I gave the next talk. And afterwards they told me it went all well and everyone was happy. I don't know if anyone learned anything.
So nobody noticed that you did a talk that you just pulled up randomly from your computer?
I promise no one noticed, and I had to change my shirt out. Otherwise, afterwards I was totally drenched. But then I thought, okay, if you can do that, then maybe don't worry.
So there you hear it, people. If you ever want the world famous quantum machine learning scientist Maria Schuld to speak at your events, just send her an email saying we're waiting for you here, and she will show up.
Yes, and or never take my talks too serious. They might just be like pulled up. No, I'm joking. Yeah, but
awesome. Maria, I know that you're a surfer, but I actually also recently found out that you were into lots of water activities, diving and snorkeling, exploring the coast. What What do you like about the water? What is so interesting about the water that draws you to it?
Oh gosh, I think it's very different. Surfing, everyone says it's peaceful and chilled and has this like a peaceful vibe of the ocean. It's completely crap. People who surf are very competitive. They have to fight themselves in the ocean every way. And sometimes you've got these moments of happy bliss. But I think anyone who's competitive loves surfing. So that's something different. And the diving and the snorkeling I've recently explored, which is maybe it has also something to do with something that draws me to science, another thing that draws me to science, which is this idea of observing. So everything is quiet around you and you just look and you just float and then stuff happens in front of your eyes. So, and I'm lucky enough to be in Durban. If the water is not too polluted, we can just go in and just dive off the coast pretty much. So that's actually really, really nice.
How warm is the Indian Ocean down in Durban?
It's too cold for me, so I'm the only person who is in wetsuits, like at least formal wetsuits. I sometimes buy my wetsuits in Canada. Actually, in Toronto, there's a surf shop that's opened by a person from Durban.
Toronto is a world famous surf capital. It's true.
I know, yes, and I would never do it there. No, we've got like 20-ish degrees fluctuating. Freeze very easily. I want to put a hoodie on, but everyone around me who surfs with me doesn't want me to do this because it's extremely embarrassing to do this in Durban where everyone's half naked, and so I kind of
Sorry, you want to surf with a hoodie on? Is that what you said?
yes, in 20 degrees. Sorry.
Interesting. I thought I was cold-blooded, but that's that takes the cake.
Yes. So if you ever want to do a big bet to me, then we can bet on me going surfing Lake Ontario in winter, which a couple of people do. I might die though.
Yeah, it's pretty cold in the lake over here right now. Awesome. So Maria, I know that Africa is very close to your heart, and machine learning is also very close to your heart. How do you tell the people about some of the things that you do, kind of maybe that they're not aware of behind the scenes that tie together your two passions?
Oh yes. So actually I don't know, probably no one knows that I'm not working for Xanadu on Fridays since many, many years. So I'm keeping this day free, and I'm doing a lot of research with psychologists and social scientists using machine learning for basically data analysis. I would say like on very local topics. So for example, at the moment we're building word embeddings that try to understand polarization coming from the recent unrests in the protests and the unrest we had last year. So there's a lot of that. I'm also quite involved in a beautiful movement called the Deep Learning Indaba. If you've ever been on a machine learning conference, you realize that Africa is really booming there. The coolest parties are done by like Black in AI and the Deep Learning Indaba. So I'm kind of part of the organizing committee for the local versions. I've done it for many years. I think by now I'm really stressed. I also have to pull apart all the budgets for the last 10 years, no, for the last 5 years, which is what I'm going to do my next weekend.
Those parties don't pay for themselves.
Exactly. It's a lot of admin work, but there's so much enthusiasm from people who are just hungry for this stuff, and it's just such an honor to be part of that community as well.
Amazing. Maria, at this stage in your career, I think it's fair to say that you might be a bit of a role model to some other younger people coming up out there. You've been through multiple stages of your career. I'm sure you've got lots of experiences, lots of tips or insights or helpful suggestions that potentially you could pass on to the next generation.
Yes. Oh my gosh. So you know that so I once was at a talk or was kind of like a fireside chat or something where someone asked me, so what's the tip for the next generation? And the one I came up with is kind of like along the lines to do your own stuff, to kind of think in your own ways, to not try to publish in Nature and do all of that stuff. And someone from the audience said, that worked for you, but it doesn't mean that works for anyone else. So I'm always a bit careful with those things. There's just a way of also enjoying the journey and not going to do the things that other people think are fancy. So don't go to MIT if you don't want to. Don't leave your hometown if you don't need to, go along your ways. For me, there's also a very cool time coming up, which is I'll go on maternity leave soon. So I'll be a first-time mom. So also this is something I'll be really looking forward to. And I hope this also integrates into science. I think science has changed enough to kind of have space for women also doing that. And so that's another thing I'm looking forward to.
Amazing. Congratulations.
After. Thanks.
All right, chat. Now it is your turn to bombard Maria with all your questions. I'm going to go back and look through the chat here for some of the good ones here, and I'll relay them to you, Maria, okay?
Shoot.
All right, we have a question from BK is from Texas. It says, machine learning itself is still a maturing technology, much less quantum machine learning. Is the technical utility of QML substantial enough to offset the learning curve and limited adoption?
So that depends on for whom, right? So if you want to, I don't know, if you are a company and you want to make money tomorrow with this, I think then you might want to invest into something else at this stage. If you are part of a movement that builds some applications of the future, and you're willing to invest a lot of time, effort, money, and sweat, and you believe in kind of like innovating in paths that nowadays you can't even see where they lead, then definitely it's worth. And also, if you want to just crack extremely complex problems, then it's also definitely worth your time. So very much depends on this. But if you're already worried, maybe, yeah, I think in quantum computing, there's not much easy topics, but maybe this is something that's only for the adventurers at the moment.
Awesome. How about we go to this question from Heisenberg's dog. Maria, you mentioned that computational complexity is a wrong tool for NISQ algorithms. Does that mean all these algorithms are heuristic?
So first of all, I don't know. I don't know if it's the wrong tool. I think it shouldn't be the only tool, or it's a very difficult tool, right? I hope this was clear that yeah, you know, from the talk. Also, I don't know if quantum computation complexity is the wrong tool for NISQ algorithms as such. I think it might be a not so fitting tool for applications research. So basically, if you are sitting there and you just want to know, like, how does my NISQ algorithm scale, you can use this as a tool if you want. But if you want to know what will make us in 5 years' time, 10 years' time, actually use quantum computers for machine learning, for chemistry, for finance, for all these real applications, I think it's a very limited tool. So I hope this kind of like clarifies a little bit what I wanted to say.
Excellent. Next question is Daniel from Nigeria. Daniel asks, does kernel-based training perform better or equally good compared to variational circuit training?
Haha, so now you're getting into my favorite topic, which I didn't talk about today. Just as a background, so I was talking about a link where we found that many quantum machine learning algorithms in this variational part, especially, or this near-term part, can be understood as linear models in feature spaces that are the spaces of quantum states. And this allows you to have a bit of a different training paradigm. So you don't train anymore the parameters of your algorithm, of your quantum algorithm, of your quantum circuit, but you train different parameters in some sense, like classical. I mean, they're all classical, but like parameters that come on top of your quantum model. So the quantum computer only does something very small in your machine learning algorithm. And about the better, I mean, you can't ask a scientist if A is better than B if something is like really big. This totally depends on the situation. What I personally have found in very, where I don't think about errors and I don't think about like, all the nitty gritty of quantum computing, what I've found that has blown me away is that if I train a variational model versus a quantum kernel machine version of that same thing, which is still subtly different what it does and finds, but still, I found that the number of circuit evaluations is a lot less in the kernel method, which I didn't expect. So I was super surprised about this. And when you think about it, it starts making sense. So at least when you have an application, encourage you to think about whether this is an alternative for you.
Awesome. We got quite a few questions about kernels, so I'm glad that we got to hit upon that one. Question from, let's go with Reckoning Sa. Why do we bother doing research on variational circuits and QML on near-term computers when we expect them to be surpassed by fault-tolerant quantum computers in a few years?
Yeah, I think one of the answers is that we need to keep the investment going. No, I'm joking. No, we have these machines, right? Like, so a big question is what we can do with them. If no one ever touches them, if no one ever like tests them on real problems, then nothing will ever happen. I mean, maybe the big computers will never be built, really from practical arguments, because no one's interested enough to invest the money. But also, we don't really know where to go to build them and what's needed to build them. Maybe we can also feed back a lot of our experiences into this. So if we don't get our hands dirty in this, so it is a nasty space. It's the space where we're kind of always limited by everything. So it's not nice. Sometimes it's very frustrating actually to do research there. But if we don't get our hands dirty, then we hit, even if someone invents a fault-tolerant quantum computer one day, it won't just like run, but we really like stop having, or we give up having all the essential bits of experience on the way there.
Yeah, I can't really think of many scientific breakthroughs that it was predicted exactly what it was going to look like decades in advance, and then we built it to spec. Like most things you would expect, you learn some lessons along the way.
Yes, and fault-tolerant quantum computers, I mean, they are a unicorn, right? They are an invention of people on paper, and nothing, everything that will get us, even if they're invented, they are messy. There's something messy on the way there, right? So we better get into the mess early than late.
Exactly. And we're still reinventing classical computing.
Oh, yeah. Yes, hardware as well, right? And think about, for example, machine learning, the hardware that people use evolves from the application. So people say we have deep neural networks, they work, they're super huge though, but we can parallelize them. So then people start like putting up GPUs and like massive parallelization, big server farms. So the hardware follows from these applications as well. So this is why it's so cool. It goes both ways, right?
All right, Mia, how about one last question from the audience? So from Xfish, we've got, do you think that feature extraction with quantum models is ever going to beat classical ML?
Feature extraction, so I assume that the I argued a whole talk that we shouldn't think about advantages all the time. So I hope I bought myself free from this question.
Yes or no, the only acceptable answers here.
Damn it. I assume that feature extraction you mean from classic. So there's a bit of a difference if we like look at classical quantum data. I do think yes, but I do think this will be very specific situations for now. And I think yes. But I think this won't be like that every machine learning application now needs a quantum computer. But I think this will be very specific ones, and which ones, that's the deal we're trying to find out.
Okay, so that was a yes, but not a very definitive one.
Yeah, of course. I'm a scientist. I can't say, I mean, I'm not a politician.
Exactly. All right, you know what, Maria? Why don't we throw in a couple more questions? I know there's a lot here, and I want to make sure we get everyone a chance to ask their questions. So you did mention a couple times, maybe obliquely, about financing and funding. So one question here from Legitimous White Lord: how do you convince finance or founding on QML projects when companies only talk about quantum speedup?
Can you say this again? So how do you motivate this to the companies, or
how do you convince? Let me see if I can paraphrase it. How do you convince people to invest in QML projects or companies when right now everyone's only talking about quantum speedups, and you say that there should be something beyond that?
So obviously, like also in quantum machine learning, everyone talks about speed up. So this is like then how people invest. But my idea, even of the investment world, so I was a bit naive about this. I always thought you have to promise the world to investors, but it's a lot more complicated than that. And there's a lot more space for different ways. So for example, if you can convince a good investor, or you can motivate that what we need to do for a while is capacity building or infrastructure building or something. And only then we will be able to figure out the real questions of how to get there. I mean, these people and the whole industry, they have seen emerging technologies already, and they know it's not just that a couple of scientists sit there, they think that they have to answer this one question and then we'll get there. So I think we're underestimating a little bit the spaces that are given to us here. And I'm also not saying in the end that we shouldn't find an answer to like if quantum is better or not. I just say that at the moment, at least 20% of all QML papers write them without the need of proving quantum advantages, right? That's all. And I think those might be the 20% of the papers that are actually important in 5 years' time. That's my statement. Maybe this was a bit more politician than scientist, but
All right.
Yeah,
We've seen both the scientist and the politician today from Maria.
Oh God. It's
all right, Maria,
QHack,
we would love to have more questions, but we do have lots of other great speakers lined up. So I would say thank you so much for joining us today. It's been really great to have you on with us.
Thanks a lot. Yeah, thanks for having me here. Have fun. I'll be watching as well. I'm very keen to see what's happening this and next week.